Okay, so our first speaker is Peter Bubenik from University of Florida, Gainesville. And he will be talking about persistence from algebra to analysis. Thank you, Peter, for being here.
Okay, thank you, Tamal, for the introduction and the invitation. It's a pleasure to be here. And today I'll be presenting joint work with Alex Elchison, who was a PhD student with me and is now a postdoc at Colorado State University. So the motivation for persistence is topological data analysis. Our goal is to use algebra to summarize the shape of data and then to analyze those summaries to answer scientific questions. So quick outline of my talk. We'll go from algebra to analysis with a detour in something called optimal transport. So let's start with the algebra. So this is a setting that's probably most familiar to a lot of people. We start off with some data and we build a one parameter family of spaces or simplicial complexes, and we compute homology to get a collection of vector spaces and linear maps. So here we have an increasing sequence of simplicial complexes. We apply homology with coefficients in a field, and we get this diagram of vector spaces. And we have this beautiful structure theorem that allows us to produce a set of bases so that the linear maps actually give us a partition of all these basis elements, and that gives us a collection of intervals, which we call a barcode. So a little more abstractly, so the setting for today's talk is that we have some underlying partially ordered set, which gives us our shape of our diagram of vector spaces. So in this case, we have, so for this talk, things will always be finite. So we have this finite indexing set of numbers from 0 through m that are totally ordered. And then our persistence module is a functor into the category of finite dimensional vector spaces and linear maps. And our algebraic summary is our barcode. Okay, now let me look at that in a little more detail. So from an algebraic point of view, our persistence module has a direct sum decomposition into interval modules. And if we just look at that collection of intervals, it's usually described as a multiset. So the multiset of intervals is the barcode. And now I'd like to advocate for a use of a synonym to multiset, which I think is much better. Multisets are formal sums. So instead of writing them as a collection of or an index set or a disjoint union, we're going to write them as a formal sum. So that's what we have here. Beta is our barcode, is a formal sum of intervals. So notice each of the x sub j's is an interval in our indexing totally ordered set. More generally, we're going to talk about posets. And the nice thing about a poset is that it actually has, the intervals in the poset have a natural metric structure. If we take two intervals, we can look at their symmetric difference. And in the finite setting, we can just count the number of elements in that symmetric difference, and that gives us a distance. In fact, it gives us a metric on the collection of intervals in a poset. And this metric has a distinguished element, this metric space, which is the empty interval. And that empty interval, when we look at the formal sum, also acts as a kind of as the zero object or the base point for the free commutative monoid on that pointed metric space. Okay, so the notation here is that beta or barcode is an element in the free commutative monoid on this pointed metric space. All right. Now, if we look at formal sums in pointed metric spaces, it has this distance that has arisen in a lot of other places, and we call it the one Wasserstein distance. So we have two formal sums, which might have different numbers of elements in it. So we can fix that by adding in, because we have this empty interval, we can kind of freely add it. It's the base point. So we add in n elements of the base point to the one sum and n elements to the other. So each of them has n plus n elements. And then we look over the symmetric group, gives us on n plus n letters, gives us all possible ways of matching these intervals, and we just add up all of those symmetric differences. Okay, that's the one Wasserstein distance. And then a theorem we proved a few years ago is that it, even though it maybe seems somewhat ad hoc, it's actually universal in a particular sense. It's given by a left adjoint to a natural forgetful function. Okay, so let's move to a slightly more general setting. So we have what we now call generalized persistence modules. So they are diagrams of vector spaces indexed by a partially ordered set. And now in this general setting, these persistence modules no longer decompose into direct sums of interval modules. However, we could still use algebra to produce formal sums if we're willing to add in negative elements. Okay, so these are signed formal sums are produced by kind of the natural extensions to constructions that we use for the ordinary persistence modules. So these I'm going to introduce briefly. So Möbius inversion and homological algebra are closely related. Möbius inversion is a combinatorial construction. So this is the general construction for a finite poset. We have for each interval in P, we have a generalization of the notion of rank of a map. What do we do? So an interval in our partially ordered set is a connected and convex subset of the poset. So it's convex, meaning if we take any two elements in the interval, all the intermediate elements are also in there. And it's connected, meaning if we take any two elements, there's a sequence of comparable elements that are inside the interval to get us from one to the other. So for such an interval, the persistence module restricts to it. Then there's kind of a universal vector space that sits on top of it, the colimit, and a universal vector space that sits below it, the limit, and there's a universal map between them. Okay, all this we kind of get for free, and we just look at the rank of that linear map. Okay, this gives us our generalized rank functions. It maps from intervals into the integers. We take the Möbius inversion of that combinatorial construction, and it gives us another function, which is the generalized persistence module. And it turns out that this is a signed formal sum in this pointed metric space of intervals on our poset. Okay, here's an example which you might have seen in this month's issue of the notices of the AMS. We have this nice picture by Woojin Kim and Facundo Momoli. On the left here, we have a indecomposable non-interval persistence module, and it has this decomposition or associated formal sum of intervals. Okay, so we have the blue intervals are positive and the red one is negative. All right, now a somewhat more sophisticated point of view. This is coming from relative homological algebra. So any category of persistence modules is something called an abelian category. And in the finite setting, we have this finite projective resolution. And we can take an alternating sum of the elements in the projective resolution, and this again gives us a finite formal sum. And in fact, there's kind of this beautiful and large generalization of this, which gives us a lot of flexibility and adds a lot of power to this point of view, which is we're free to choose any exact structure on this abelian category. All right, so let me show you a picture. That was a lot of math in one slide. So here's a picture coming from a paper by Botnan, Opperman, and Udo. Again, we have a indecomposable non-interval persistence module on this post set. There's a 3x3 elements. If we take the resolution to the rank exact structure, then we get this finite formal sum. So we have positive elements on the top and negative elements on the bottom. All right, so to summarize, generalized persistence modules have algebraic summaries consisting of signed formal sums, and using this simple definition, Alex and I showed that we can extend the one Wasserstein distance to signed formal sums. So we just take the negative elements and we move them across to the other side, and then this definition reduces to the usual one Wasserstein distance. Okay, so that gives us a metric space on signed formal sums. And now looking ahead to the second half of the talk, what we want to do for learning is we want continuous maps on this into the real numbers. And then if we have a collection of those, that gives us then a vector from our generalized persistence modules. And then that vector summary is something that we can feed into machine learning algorithms. Okay, so a short detour into optimal transport theory. So this was initiated by Gaspard Monge in 1781, and it's a very applied problem. We want to move material from some collection of locations to another set of locations. So we have inputs and outputs, and we have various transportation plans for moving our material from the input locations to the output locations. And each of these has a cost associated to it, and the question is, what is the transportation plan with the optimal cost? Okay, now the modern point of view of this problem was given by Kantorovich, who gave a measure theoretic interpretation of this. So we have a complete and separable metric space with two probability measures on it, and so we're working in the space of all probability measures on a metric space. And our transportation plans are given by couplings. So these are probability measures in the product space, whose marginals are the input and output probability measures. And the cost of our coupling is given by integrating the distance function. And the Wasserstein distance is the infimum over all possible couplings. Okay, so the theorem is that this gives us a metric, it satisfies the triangle inequality. And furthermore, there exists an optimal coupling. Okay, so the main part of the work that I want to show you today is a relative version of this that Alex and I have developed to address the situation arising in persistence. So this is the way I would describe it to Gaspard Monge. We have a bunch of inputs and a bunch of outputs, but we have an additional item, which is we have a reservoir in which we can borrow material or to which we can dump excess material. So we have this kind of source and sink available to us. And again, it's an optimal transportation problem. What's the optimal, what's the minimum cost under this situation? Okay, now if I were describing it to Kantorovich, we have this more measure theoretic setting, and this is, of course, is the real definition. So the setup is that we have a pointed proper metric space. Proper means that closed balls are compact. This gives us another number of, well, it's technically useful in itself, and it also gives us that the metric space is complete and separable, locally compact and sigma compact. So all these are useful things. And now we have an analog of probability measures, which is something we call weakly finite weak radon measures. Maybe I'll say a little bit more about that later. Otherwise, the definition follows exactly the same as before. We have couplings, which are these measures in the product space with the given marginals, and the Wasserstein distance is kind of the lowest cost over all of the couplings. Okay, and the theorem is that this gives us a metric. It satisfies the triangle inequality. That is hard to prove. And furthermore, there's an optimal coupling. Okay, and now what's the connection to the signed formal sums that we had earlier? Well, we think of those as being signed sums of Dirac delta measures. Okay, so each of the points in our pointed metric space or bars in the barcode, we think of them as being a measure of mass 1, kind of concentrated at that point. And then we have this sum of them, which is just the sum of the corresponding measures in the metric space. And the definitions of one Wasserstein distance here agree, so we have an isometric embedding. Okay, so as often happens in mathematics, we've moved to a bigger setting with maybe more structure, and this is going to help us understand all of the functionals on this space. Okay, so now we want continuous maps from this bigger space of these radon measures into the real numbers. Okay. All right, so that moves us to the final part of my talk, which is analysis and specific. So analysis is in TDA, but there's a large community of people who've been looking at analysis for a very long time, which is functional analysis. And our community is kind of not, I think, taken full advantage of a lot of the ideas coming from this subject. And maybe part of that is because the translation between the two is kind of not exact. And Alex and I think the one interpretation of this work is really kind of bridging the gap between these two subjects. Okay, so this is my main slide for the talk. Actually, this is the classical version of the main slide of my talk. Our version will be next. And this is a beautiful result that you may not have seen before. It goes by the name of the Rees-Markov-Kakutani theorem, and it gives us a tight and beautiful connection between measure theory and functional analysis. So the setting is usually given these days as a locally compact Hausdorff space. And we're interested in looking at real valued, compactly supported continuous functions in this space. Okay, that's a vector space. Has a linear structure. So that's one vector space. And then the other vector space is the vector space of measures on this metric space. And it's kind of nice measures. The terminology is the radon measure. So what is that? That is a measure on the Borel sigma algebra. So these are, this is the sigma algebra coming from the open sets in the metric space. And they have some kind of nice technical properties. They're locally finite, and there's something called tight, which is that they're irregular on Borel sets. So any Borel set that measure can be approximated from below using a measure on compact sets. Okay. So a lot of that is stuff that can take a semester to explain very carefully. But the punchline is this beautiful theorem. So the Rees-Markov-Kakutani theorem. So if we have any continuous linear functional on this metric space, so anything of this form, there is a unique radon measure so that linear functional is given by integrating with respect to that measure. Okay. And furthermore, it's actually an if and only if. The other direction is easier. Integrating with respect to a measure is kind of automatically a continuous linear function. Okay, so these two things are equivalent. And in fact, Bourbaki uses this equivalence to build up measure theory just from this theorem. Uses that as a definition for radon measures. Okay, so now we have a relative version that I'm very excited about. So in this case, the setting is that we have pointed proper metric spaces. And so we have a bit more extra structure than in the previous slide. We have a metric, and that allows us to restrict from continuous functions to Lipschitz functions. So these are functions that are well behaved with respect to the metric. So they're functions from our metric space into the real numbers. They're non-expansive, so they kind of can only shrink distance. And we want them to be pointed because we have a base point to work with. We can insist that that base point is sent to 0 in the real numbers. Okay, so again, this is a vector. These assemble into a vector space, and now we have this vector space of the appropriate notion of measures in this setting. Okay, so what are they? So they are again measures on the Borel sigma algebra. They are locally finite away from the base point. They are also tight, and then at the we need some control of things at the base point, and that is given by saying that they integrate the distance function. All right, so this is somehow, if you're familiar with persistence diagrams, this is somehow controlling. So the measure is allowed to kind of blow up at the diagonal, but in a controlled way. Okay, so our theorem is again an analog of the other one. We have this very nice one-to-one matching between continuous linear functionals on these this vector space of pointed Lipschitz functions and our radon measures. And again, this is a one-to-one correspondence. And we get one other really nice thing that I'm also excited about, which is that the operator norm of this continuous linear functional is given by a generalization of the Kantorovich-Rubinstein norm. And this one is kind of more flexible because so we have just an arbitrary signed measure here, something slightly more general than a signed measure, and we just take the positive and negative parts, and we take the one Westerschein distance between them. Okay, so there's a lot there to digest. It should be on the archive soon. So to summarize, let's go back to persistence. So if you're paying very careful attention, you notice that actually I kind of did the opposite of what I intended to do. I was looking for functionals on these radon measures, which contain signed summaries of persistence diagrams. And instead, I showed that they were functionals on something else. Okay, so instead of finding the dual, I found the pre-dual. But that's okay because the dual of the dual is something that we can do. So, so since these pointed Lipschitz functions embed in the dual of their dual, they give us what we're looking for. Okay. So the punchline is that if we want continuous linear functionals for generalized persistence diagrams, what we should be using is pointed Lipschitz functions. Okay, and with that, I'll end my talk. Thank you very much.
Any questions, please? Yes.
I don't get why where's the point that
Can you speak to the microphone there, because otherwise.
yeah, my question is I don't get why we need pointed spaces.
Pointed spaces, that is a great question. So yeah, so let's go back here. So when we look at direct sum decompositions, so I'll start with algebra, if you're happy with algebra. If we take direct sums of vector spaces, for example, we can get a bigger vector space. And one thing we're free to do is there's also kind of this trivial vector space, which is the zero vector space. If we add in a direct sum of a zero vector space, then we don't change anything. So this happens this is ubiquitous in algebra, that there's kind of this zero object. and adding in the zero object doesn't change anything. So that's kind of where it's coming from, and I think in analysis this tends not to happen, or at least it's something that people haven't used. And the main thing that kind of persistent homology and TDA is contributing to analysis is bringing in this algebraic setting where we have a zero object. Okay. In the more combinatorial setting of a formal sum of a barcode, we have a collection of intervals. I can add in empty intervals without changing anything. Okay. And if you're familiar with the persistence diagram point of view, sometimes people add in dots on the diagonal. That's related to this story. We're kind of adding in zero elements, and we're kind of free to do that. And that's really, that freedom is really what allows us to have this one Wasserstein distance, which allows us to compare things with different quantities, which we don't get in the usual kind of probabilistic framework where things have to have equal mass to be comparable.
Another question, please.
Yeah, I want to comment on your version of the race representation you were asking. Is that paradoxical? So for example, if the metric space is the real line, the thing is going to zero, then the matrix function, you can define a linear operator on the matrix function differentiating your matrix function, integrating against the derivative against the four elements. Would that such a function will be representable in the integral of the function again? Yeah.
So so I think that's a good idea. The difficulty is really at that base point. So I think we should talk some more to see if that's feasible. But so at that base point, things blow up, and so if we take any ball around the base point, the measure is allowed to be infinite. And then in our setting, we are allowed to take differences of those things. So they're actually not signed measures in the usual sense. So yeah, we should talk some more after this talk.
Are there questions on the?
Yeah, there are two questions on the chat.
Okay, please.
What is the distance in the pointed metric space given by the intervals of the poset?
Sorry?
What is the distance in the pointed metric space given by the intervals of the poset?
So we look at the symmetric difference. So I don't know if people can see me online. So if we have two intervals in the barcode, we look at their union and we subtract their intersections. That's the symmetric difference. That will be some number of intervals between 0, 1, and 2, and we just take the lengths of all those intervals and add them up. So that gives us the distance between two intervals. In the more finite setting of a poset, the two intervals are just subsets of the poset. Again, we take their union and we subtract their intersection, and then this is a subset of the finite poset, and we just count the number of elements.
Then there's one more question. Are there any conditions on the measures with respect to the base point, x0, y0 in your definition? Are there any conditions on the measures with respect to the base point?
Yes. Yeah, so there's these technical conditions that I call the weakly finite weak Radon measure. I think it's easiest to describe in terms of persistence, in terms of generalized persistence diagrams or persistence, which people are maybe more familiar with. One way to get these is we take finite persistence diagrams or generalized persistence diagrams, and then we take their Cauchy completion with respect to the one Wasserstein distance. So we're allowed to start adding more and more points close to the base point. And we can add countably many points as long as the it only takes us a finite amount of work to push them to the base point. Okay, so we can have this kind of blow up of having infinitely many points close to that base point. As long as the Wasserstein distance stays finite.
Okay, with that one, let's thank Peter. Thank you.